So today I have to go somewhere, so I will start because if I wait now, I may not be able to finish my 7. So anyway, let's start. So the typical format is as usual. First, we'll discuss some uh, theory points that were discussed in the last classes.
Hello, sir. Hello.
Narendra. Ah,
Good evening, sir. Good evening, sir.
good evening, Narendra. Where are you?
Okay, I'm here. Fine.
Last time you were Rasika, now you are back.
Ne, actually, in the last time, I was out of station. I was in actually in some program, and
Yeah.
there was a lot of any disturbances. Even though I joined your in a class with
You have
my daughter's ID.
Yeah, I was just joking, okay? Anyway,
Then,
so
okay.
uh, Priyanka is also here.
Yeah.
Actually, today I have to go somewhere at 7 o'clock, so
Okay, okay, sir. No
I'll
problem.
be slightly fast today. If you
Okay,
have
sir. No,
any
no,
issue,
no, sir. No problem, sir. Okay.
yeah, if you have any issue like Narendra or Priyanka, you can tell me, okay? But we'll
Okay.
start.
Okay.
So, first is
Yes,
a
sir.
brief revision. I saw that there was one topic, thermodynamic relations, but none of it was asked in the assignments. So anyway, there are some important concepts there. I'll just tell you what to know that may help you or anyone who will be watching this video later. Uh, I will not go into the derivation part because that was already done by professor. So very important is this Maxwell's uh, relationships or equations. Generally, they call it relationships, but here in this course, it can be called as equations as well. So this is important because I have seen some competitive exams in MCQ type papers. They will just give you 4 options, and you have to choose which of them are Maxwell relationships. It can be as easy as that, but sometimes it can be difficult also in mostly in subjective papers. So the trick that I used to remember it was if you remember correctly, there are these 4 quantities that we generally associate Maxwell's relationship with them. So there are 2 ways to remember this. Uh, One is Tapasvi. So basically, in clockwise sense, one second. In clockwise sense, if you want to remember, this is a better way. One way is to remember Tapasvi word, so that T P S V everything comes in a circle. Or you can remember this sentence also, which was thermal power station in village, something like this. So TPSV. So you can remember this also, whichever is easy for you. Tapasvi, I feel it's easier because I remembered it during my gate days. Now also I remember it. So the trick is write this way: TPSV, Tapasvi. Make sure it is clockwise. And another thing is when T and P are on opposite sides, add negative sign. So opposite sides, that means like one case shown here. So then only you add negative sign. If T and P are above each other, you don't add negative sign. So these 2 things, if you remember, you can remember these Maxwell's relations. For example, TPSV, first case, this will be del T by del V at constant S. And since P, let's write the second term, del P by del S at constant V. But since T and P are on the opposite side of equality, add negative. So this will be your first relation. Then rotate the alphabets. So then write T here, P here, S here, V here. Then it will be del V by del S at constant P equal to del T by del P at constant S. So here T and P are above each other, so no need for negative sign. Now change it. Now let's take T at the third quadrant, TPSV. Then again you can write del S by del P at constant T equal to del V by del T at constant P. Uh, Here T and P are on the opposite side, so you have to add one negative sign here. Then the last one is T P S V, Tapasvi. Then you can write del P by del T at constant volume is equal to del S by del V at constant temperature. Here T and P are on the same side, so no need of negative sign. So if you do this way, you can remember all four Maxwell's relation. I hope this will help to those students who at least attended my class. So yeah, this is for Maxwell's relations. Then there is something called as Helmholtz free energy, Gibbs free energy. I don't know how much of that is useful in your graduate level exams for mechanical engineers. Maybe for chemical engineering it will be useful, but for mechanical engineers it is not that important. But anyway, you should know Gibbs free energy. This is important concept for chemical equilibrium. So it is generally G equal to H minus Ts, and Helmholtz free energy. It is sometimes people write H, but they get confused with enthalpy. So I think that's why professor has used A here. So it will be A is equal to U minus Ts. So then you can use those TDS relations and you can do all sorts of things here. And as a consequence of these manipulations, you get an important equation for Clapeyron equation. Uh, it is valid for phase change. I mean, I should not say that this way, but generally it is used for phase changes. So it is like one second. Yeah, so the final form is like this: d ln p by dt equal to hfg of that phase change and r t square. This is for gas, like I mean, for liquid to gas. Uh, in general, you can write it as hfg by t into vg minus vf. I mean, this is for ideal gas. In general, you can write vg minus vf. Those things were discussed by professor, so I'm not going into details here. Uh, then, yeah, there is one more thing is that from these relationships you can derive du as Cv dt for ideal gas, and these both terms Cv and T, they are both function of temperature. That's why you say for ideal gas du is function of temperature. Th is also Cp dt for ideal gas, and as it turns out, there is one more relationship which is I think in class it was shown like Cp minus Cv as some three terms. One second, I'll just write Cp minus Cv as this. One second. Yeah, minus T del P by del V del V by del T square at constant pressure. So from here, one thing you can show is Cp minus Cv for Cv equal to R for ideal gas. So their difference is constant, but they can be function of temperature. So that you should remember. And also by some other manipulation, you can show that Cp minus Cv is a function of temperature for in general, like not only for ideal gas. In general, no. For ideal gas, it can be shown as function of temperature. Uh, there you use some this thing, compressibility and all those things, and then you show that Cp minus Cv is function of temperature, and their difference is constant. So therefore, they both are function of temperature, and that's why these two are true. So for ideal gas, U and H are function of temperatures. So these two, I mean, from those two lectures, I mean, there are many things that you can do with the thermodynamic relationships, but I think for undergrad level, this much is required, and that's why it was discussed in those two lectures. But I feel You should know these things going forward. Most important is this Maxwell's relationship. So if I want to let you take one thing away from these two classes, is this Maxwell's relationships and how to remember them. Then the next part, which is actually important for today's discussion, is this air standard cycles. So for them, the most important thing that you should remember is assumptions. I'll not write them here because that will take a lot of time. But essentially, we try to mimic the real life machines like SI engine or petrol engine or CI engine, which is diesel engine. Those are real life things, real life machines. But we can't if you want to study them thermodynamically, you have to define a standard cycle which is which can be assumed as internally reversible, and then only you can analyze in thermodynamics. Otherwise, you can't write because the state points will be not defined properly. So that's where these air standard cycles come into picture. So you should remember all the assumptions. I think there were 5, 6 assumptions. Most important is all processes are internally reversible. So I'll just write down the important ones. All processes are internally reversible. This is the most important that I feel you should always remember, because otherwise the whole analysis will be null and void. And for this auto and diesel, you take it as a control mass. So your air, which is being compressed, expanded, uh, that is that is same. So therefore, you take it as a constant mass system, and composition also you assume same. In reality, it is different because after combustion, the composition of air changes, right? But still, you assume it as the same. Uh, Again, you assume CPCV constant, uh, and you neglect kinetic energy and potential energy changes. So these all our assumptions are there, but what I feel is this internally reversible is the important one. And yeah, I mean, if not anything else, you should at least remember this one. If for any interview, if you are appearing, you should if it comes to air standard cycles, make sure that you mention that these are internally reversible processes. Then only all the derivations that you did are valid. So first was Otto cycle. It is relevant to petrol or SI engines. We call it spark ignition engine. These are conventional terms. Nowadays, everything is a mix of everything. But earlier, when these two terminologies were distinct, that time Otto cycle was for SI engines. So here you should not forget. I think you will remember that generally we plot PV to get net work done under the curve, and TS to get net heat interaction. So these two plots are important. And why important? That you should also know. First we compress the air, then we do constant volume heat addition, and then there is expansion, and there is this thing, constant volume heat reduction. So these processes 1, 2, 3, 4. I hope you remember what are all this. That is actually this is a part of power this thing, IC engine subject, separate subject it is usually taken. But since here it was discussed, we can quickly go through this. This will be PV power gamma. This is also isentropic process, uh, reversible adiabatic, and these are constant volume processes. So you can do this way. Uh, and similarly, if you go to the TS plot, it should look like this. Uh, don't These are all schematics, okay? Don't take them on the face value. These lines are never parallel. In this figure it may look like it because of my drawing, but in reality they are not parallel, okay? Some people get confused there also, so please, you should not at least get confused here. And there will be heat addition here, there will be heat rejection here, and this is your work uh, what should I say? Sorry. Uh, this is your in this process you get the work out. This is the expansion process, and in this compression process you have to give work in. So W net is difference of this work out minus work in. And since this is a work producing cycle, this difference should be greater than 0. Then only it makes sense, right? And so since this 1 to 2 and 3 to 4 are isentropic processes, area under the TS plot will give you net. This will give you net heat interaction, which will be QH minus QL. So yeah, then there is a derivation for efficiency of this cycle, which is I mean it was done in class, so I'll not repeat it, but it goes like this: gamma minus 1, where this compression ratio is V1 by V2. So generally there is this term which is called as clearance volume, so which is V2. So if you see some examples, we'll see some examples. So there are in questions they'll not give you language as V1 and V2. They'll say the stroke length is this much, the clearance volume is this much. So you have to calculate V1, V2 based on that. So if I can show it here, I apologize for cluttered figure, but this is clearance volume, and I think this whole length is stroke length, something like this. We'll come back to this while we solve the problems. Yeah, so then this is for the Otto cycle. Then there is second one is diesel cycle. And this efficiency will be equal to net work done upon total heat added. So that is also important to remember. So yeah, then there will be diesel cycle. It is relevant for CI engines or diesel engines. Only one process is different in this cycle is the nature of heat addition process. Why it is different? Because I mean it is because of the nature of the process or the nature of the machine itself. So basically, in case of diesel engine, you don't compress the air fuel mixture. You just compress this thing, air, and therefore when the fuel is added or sprayed in the compressed air, there is some lag before the combustion actually starts, and therefore this process represents constant pressure process more than constant volume. In case of Otto cycle, you compress air fuel mixture. So as soon as you do sparking, the whole mixture burns quickly. So you can approximate this combustion process as constant volume. But in case of SI engine, due to the nature of the machine itself, you cannot assume that. So the more practical assumption will be constant process heat addition. So that's why you will have the horizontal line 2 to 3. Other things remain same in both the cycles. So yeah, the same thing. 3 to 4, 4 to 1. Yeah, and you should know on TS plot the slope of which line is more. I think slope of C volume, constant volume line is more. V equal to C. Here 2 to 3 is constant volume, constant pressure. 1 to 4 is as usual constant volume. Its efficiency is 1 minus same. This term will remain same. But here one additional term comes, which is cutoff. I think it is cutoff, right? Compression ratio, and then there will be this thing, gamma C, sorry, RC, cutoff ratio only, I think. Maybe I'm not remembering this thing correctly, but yeah, there is one additional ratio there comes, which is like this. The name, I think it is cutoff ratio. Maybe you can remind me later. So it is something like this. Gamma is same as V1 by V2 as earlier. Gamma C is P3 by V2. So because here this V3 term is important here because of the nature of the heat addition. It is relevant to that. So that's why it comes into the efficiency calculation. Then there is one thing important to notice.
Sir, hello, sir.
Narendra,
Uh, I think one term is missing here. I think it
one
is
time.
a 1 upon gamma.
Okay, okay. Sorry,
And
sorry.
this cutoff ratio is it is a ratio of the volume V3 divided by the V2.
Yeah, that is what I have written,
Yeah.
right? V3
Yeah, heat supplied after divided by before. Right.
Okay, okay.
V3 divided by the V2.
Yeah, that is what I have written, right? V3 by
Uh,
V2. So yeah,
yeah,
so
yeah. I am seeing V1, sir.
sorry, sorry.
Actually, there is the V3. You are correct, but I am looking at V1. That's why I put up.
Yeah, yeah. No
Okay,
issues.
okay.
So yeah, important thing is, see, there are these two cases or many cases where you compare efficiency of diesel and auto cycle. Uh, what happens? This mathematical derivation was done by professor. This term, this gamma c power, RC power gamma minus 1 by RC minus 1. This term, if you expand, it is a term which is greater than 1. So therefore, let's put O for auto and D for diesel. So on the face of it, it looks like efficiency of diesel cycle is more lesser than the auto cycle. But this is only true if you have if same compression ratio is used. But if you remember, in the auto cycle, you have compression ratio of about 7, 6, 7. But diesel cycle, it is more than 13, 14. So from a competitive exam point of view, this case will happen only if same gamma is there, same R compression ratio, not gamma. In all other cases, efficiency of diesel cycle is more than efficiency of auto cycle. Almost all other cases. You can manufacture one hypothetical case, I don't know, but as far as what I've seen so far, only in one case auto efficiency is more, and all other cases the diesel efficiency is more. So that is one thing. Then there is one dual cycle also. uh, I would not have time to go through the derivation for the efficiency and all, because it was not part of this syllabus here. But I would urge you, if you have time, uh, please look into this. And there is efficiency expression also that you should remember for GATE or any other competitive MCQ type of exams. I have not gone through the at this point. I actually today I had a little time. I was running late from somewhere, so I could not get the efficiency expression. But you can get it easily from internet nowadays. But you should remember it. It is similar on these lines only. There will be some additional term with the new ratio. One alpha ratio will come there because of at what point of time you stop your heat is added. I mean, out of total energy or the heat that is added, for how much part was the heat added at constant volume, and for how much part it was added at the constant pressure. So to distinguish that, there is one alpha term, one more ratio it is defined. So that you can look into. If we go into that, I think we'll be crossing our time limit today. But anyway, this is the constant volume process. This is constant pressure heat addition. Other things are same only. So you should remember this dual cycle is also there, and its performance is more or less lies between auto and diesel. So in almost all cases, you don't need to study its performance separately for such comparative questions. The dual cycle will always be in between. So therefore, that part is also not that critical. Only that there is one expression for efficiency, and you should remember that for your exam. How to remember that? You can devise your own tricks, like Tapasvi. These are easy tricks. Yeah. Then finally, we have this Breton cycle. Actually, there are two versions of it. One is called as open Breton, one is called as closed Breton. So if you have this, like generally you'll have compressor, then combustion chamber, then turbine, and then cooler. So if the same working fluid is circulating through your cycle always, this is called as Joule cycle also sometimes. So if it is same fluid going through the cycle always, then it is closed. But if it is not, then it's open. Here we study, I think, closed one. So it should look like, oh sorry, here the last 4 to 1 process is also like this only, constant pressure. This is also constant pressure. So pardon my drawing, but these lines are only schematic. Okay, in reality they will not look like this. This is PV. This is PV power gamma equal to C. This is also PV power gamma equal to C. This is QH. This is QL. This is W out. This is W in for compression. So that is how you can draw it. On TS plot again, it is more or less similar. 1, 2, 3, 4. These are isentropic, vertical lines are isentropic, reversible, adiabatic. And 2 to 3 is a constant pressure. 1 to 4 is also constant pressure. This is a TS plot. So here one interesting thing is there. Its efficiency derivation is there. You can just use efficiency 1 minus 1 upon gamma P, gamma minus 1 by gamma. Here it is defined in terms of gamma P, which is pressure ratio P max by P min. From figure you can see P max is P3 and P min is P1. Here it is defined that way. You can define it in volume terms also. There is nothing wrong with it, but generally it is defined this way conventionally, so that's why we are doing it. Then there is one derivation for maximum work, net maximum work output. If you do that, you get something like this. Remember this also, okay, for your competitive exams. This if maximum work output and maximum efficiency. These two things you should remember. These two formula, remember, because if it will be directly asked in the exam, if you don't know the formula, you will spend most of the time deriving it, and it's a very tedious derivation in the exam, and most likely you will commit mistakes. So please remember this. And now we'll start the problems. I hope I have not taken much time here, but I think it's important to discuss what you have learned. We'll start with the one question which is for diesel cycle. I will read out the question. I could not get the printed version of it, so forgive me for that. There is a air standard diesel engine which has compression ratio of 13. At the initial stage of compression, the pressure is 200 kilopascal, temperature is 300 Kelvin, and maximum temperature during the cycle is given as 1500. Assume air to be an ideal gas with constant CVs. And you have to first calculate air temperature at the end of compression stroke. It's a multi-part question, okay? It's not a single part. Then you have to calculate heat transfer added, QH, that we have discussed. Then actually, see, we'll solve everything, okay, here. More or less we'll convert, like, we'll study everything. So that if you solve any MCQ type of questions, more or less one part of it will be asked somewhere. So let me write down what is given. It is a diesel engine, so we'll be using diesel cycle. So let's draw. I mean, we have already drawn it, but for the sake of this problem, we'll quickly draw it. So as you know, for diesel engine, there will be constant pressure heat addition, and it will look like something like this. 1, 2, 3, 4, 1, 2, 3, 4. And one more thing, since these are work producing cycle, it should be clockwise always, the direction of arrows. And if it is a work consuming cycle, it should be counterclockwise. So here, given data is You have compression ratio of 13 at the initial beginning of compression stroke. The pressure is P1, which is 200 kilopascal, and T1 is 300 kilopascal Kelvin. One more important thing to remember is when you solve this type of questions, always take temperature in Kelvin. I have not cautioned you about this in previous classes because there maybe at one place or another you have to use ideal gas equation. But in this type of questions, you are always 95% of the time using ideal gas equation for some manipulation, and therefore it is better to take Kelvin everywhere. Do not even think about degree Celsius. If it is asked in the problem specifically, then you convert Kelvin to degree Celsius by subtracting 273. Otherwise, keep everything in Kelvin. Then, yeah, Tmax is given as 1500 Kelvin. So, I think by this time you should know that Tmax or Pmax will be achieved at point number 3, which is T3 here. Now R is given for air, and you can assume it as ideal gas. So those things are given. Even if they are not given, we generally assume them this way only. This is the data that is given. So this is what it is. So will this solve this problem completely? Because like some part of this will be asked in some of the questions. So instead of going part wise, I feel we can solve everything together. That will cover everything. And say similar, this thing will go for auto cycle. Only the efficiency formula is different and one process is different. Other than that, everything is similar for diesel auto. Okay. So now we have P1, T1, we have T3. So now what we can do, just one more thing is for these type of problems, just go in the sequence 1, 2, 3, 4. If you are stuck somewhere in this sequence, then only try to go to the next point. So we have everything at 1. We need P2, V2. Sorry, P2, this thing, T2, right? So what we can do, at point 1 also we don't know volume. So let's first calculate that. We'll calculate specific volume here because there is no mass or work. Everything, like nothing is mentioned in joules or watts, right? I mean, so here you can go with the this thing per kg basis. That will be sufficient. So now we can assume air to be ideal gas, and from ideal gas equation, putting these values, we'll get the V1. You can cross check these values once by trying yourself. For the sake of conserving time, I'm giving you the direct answers. So now at state 1, PVT. So everything is sorted there. Now let's move to second state. You don't know P2, V2 or T2. Everything is unknown, right? But what we know is it's a isentropic process, reversible isentropic process. Sorry, reversible adiabatic, which is isentropic. So therefore, we can use this relationship. Like basically, it is S1 equal to S2. And from ideal gas equation, you can use T1 by T2 is V2 by V1 power gamma minus 1. I hope you guys know this. And what is gamma? Gamma is Cp by Cv. What is Cp? Cp is Cv plus R. So Cv and R was given. Therefore, gamma should be 1.4. And if it is not given for air, gamma is 1.4 only. This also you can remember. So now, what do we know? We know T1, we know V1. V2 is unknown, T2 is unknown. But in the question itself, it was given that compression ratio is 13. One second. Yeah, compression ratio. So this is not gamma C. This is just R. This is not RC. So 13 is if you see the definition of compression ratio, it is V2 by V1. So from here you can get V2 also. For the sake of uniformity, we'll use capital V uh, symbol everywhere. Is it required? No. 1 second. Uh, I mean, see the volume here, you can take everything in kg basis, okay? So I can write this as V1 also, just to maintain uniformity of symbols.
Sir, isn't it V1 by V2?
Yeah. Sorry. Uh, this is V1 by V2. This is a good point actually. Uh, all the ratios that you see in IC engine, they are always greater than 1. This compression ratio is always greater than 1. Cutoff ratio should be always greater than 1. And one more ratio that will come into the dual cycle, that is also greater than 1. So if somewhere you are getting confused, take everything as greater than 1 and then you can remember easily. So you need not to remember it as V1 by V2 or V4 by V3. You just remember that it is greater than 1. So whatever is the higher volume, that should come in the numerator. So see, then you can get, V1, right? So you can get V2 also if asked. That value will be something in meter cube per kg, right? And it will be V1 value divided by 13. So I'm not giving that value, it is straightforward. Now coming back to the, so you know V2 now. Now you want T1, T3, right? Sorry, T1 and T2 and P2. So now use this equation. Here, if you put T2 like this, it will be T1 divided by compression ratio power gamma minus 1. So if you do this calculation, you should get 1 second. It is not divided by, because it is V2 by V1 here, right? So when it goes to the numerator, it will come multiply. So it should be gamma power, R power gamma minus 1. So that you can put those values. What is it? 300 into 13 into raised to power 0.4. So it comes out to be at 36.95 Kelvin. So you know T2 now. So now can you get P2? That is the question. So again, you can use this. This is 1 to 2 is isentropic reversible adiabatic process, right? So we know that P power gamma equal to C. So that way you can calculate P1 by P2 will be equal to V2 by V1 gamma. So now you know this is actually 1 by gamma, 1 by compression ratio power gamma. So from here you can easily get T2 also, right? So that thing also you can calculate. It will be in kilopascal if you put P1 in kilopascal. I am not giving values because actually in this question all this data is not asked. In this question only T2 was asked. But I am just giving you ways to solve everything. If other thing is asked, how do you do it? So these numerical values you can fill yourself. I think you can do that. That's not that hard. Now let's go to third point. So third point is straight away because P3 is P2. It's a constant volume heat addition. So one parameter you got here itself. T3 is Tmax, which is given as 1500 Kelvin. That was also given in the question. So from here itself you can calculate V3, which will be RT3 by P3, right? It will come something in meter cube per kg. So the third point itself, it was easier to derive because T3 was already given and P2 was equal to P3. Now come to the fourth point. Now fourth point, is anything given? Uh, what, like, 1 second. Yeah, so again, for this process 3 to 4 is again, uh, 1 second. 3 to 4 is again PV power gamma. So then again you can use that T3 by T4 equal to P4 by V3 power gamma minus 1. The same relation we used initially, right? For between 1 to 2. Here it's like not between 1 to 2, it is between 3 to 4. Now this V4 by V3, if you look at the uh, figure, you know V4 is equal to V1. So you can write V1 by V3 power gamma minus 1. You know V3, you knew V1 from initial points, so you can get V1, V3, right? So if you do that, T3 you already knew, then you can get T4. So now at point 4, you know T4, V4 is actually V1. So that is already known. What you don't know is pressure. So now again use the same trick that we used here between 1 to 2. You can use, since this is a PV power gamma process, what you can do is, 1 second, I'll write here. What you can do is P4 by P3 will be equal to V3 by V4, and again V4 is equal to V1. So same, this ratio, this V3 by V1 ratio is circulating everywhere. So if you do this calculation, you should get P4 because you already know P3. So this some kilopascal value you will get. See here you calculated P3, right, which is equal to P2. So you plug in those values in this equation and do calculations properly. You will get the P4 value. So now at all 4 points you know P, V, T. So now your problem is solved. If anything is asked, you can calculate. So now let's say if it asks that what is the net work done, because in only 2 processes there is work done, right? No, actually in 3 processes there is work done. So one approach could be to calculate work done during compression, then during heat addition, it is PdV, so P delta V it will be, and then work done during this thing, your expansion. So it will be 3 to 4. Work done due to 4 to 1 is 0. So now here you give work done to the system. So this quantity will be negative according to our sign convention. This should be work done on the system, right? Because you add the heat, sum of the heat, and this is work done by the system. So I think these will be the signs, and this is one way, but another way could be what you know, efficiency of diesel cycle is net work done upon total heat added, QH, or here it will be Q223. So here it is easier, right? You can use that formula that you have written some time back. Gamma minus 1 by gamma compression cutoff ratio power gamma minus 1 by cutoff ratio minus 1. Because here this was given in the question itself. This is V3 by V2. So you know V3, V2. So RC, RC you already know. So by this calculation, you can directly get the efficiency value. And now your job is easy because now if you want W net, you just have to do efficiency into Q223. Now Q223 will be Cp T3 minus T2 because it's a constant pressure process. You can use Cp T3. So by this way, you can calculate everything. So if you do the calculation, uh, you should get the value of efficiency as 59%. This efficiency, if you do everything properly, I'm giving you this value just for the sake of cross checking. You solve it yourself, you should get 59.16%. And this QH should be around 665.7 kilojoule per kg. And therefore, your net work done should be, I think it is around 393.8. So please do this problem once honestly, and you'll get these values. So yeah, this is how it is. And in general, if it is asked, like for example, 1 second, let's say it is asked like, this process 2 to 3, it is a heat addition also, and there is some work done also. So if it is asked like some specific to that process, if something is asked, what you can do is you can use first law of thermodynamics for process, let's say 2 to 3. This will be very rarely asked, but if it is asked, you can use your first law of thermodynamics directly. Then you can write Q 2 to 3 is 1 second. 2 to 3 is U3 minus U2 plus W 2 to 3, right? And this will be your CV T3 minus T2. This will be your P2 V3 minus V2. This will be equal to P3. You can use anything, it is same. Then you can get this. And for Q, you can use CP T3 minus T2. So, I mean, see, if it is ideal gas, you can just write it as R T3 minus T2. So, essentially, it is Cp equal to C plus R. So, in some question, out of these all variables, one will be not given. So, you have to calculate this way. So, I hope you are getting my point. So, yeah, this will cover most of the problems. One more thing is, they generally ask this something called as mean effective pressure. So what happens is, like as far as I know, there are two things that you should remember. This is hypothetical value. So I mean, if somebody asks you in interview that how will you measure mean effective pressure, do it by doing experiments. You can just say, sir, it's a hypothetical value. It's not a real value. Like it's not a real parameter that you get out of experiment. It's a hypothetical value used for comparison purpose of comparison of different engines, you can say. So basically, you can use P defective ME as a symbol. So it will be PME is equal to net work done upon this thing, this stroke volume, which is V1 minus V2. So what happens? How do you use this for comparison? What you do, you fix the stroke volume. Example, this is an example. In reality, it may be different. The way it is determined is this only. So for two engines, if they have same stroke volume, if one engine is giving higher network output, it will have higher mean effective pressure. So that engine is better. So that's how you can compare. So basically, whichever engine has higher mean effective pressure, that is better, considering same stroke volume or same network done output or something same you have to give. So that's how it is. So for this problem also you can calculate mean effective pressure, and W net I have already given you the value, so it's basically just a division of two numbers, and it is the in 1.3 kilopascal. You should get this value here. 1.3, correct. Yeah. So these are all. I have taken this diesel cycle because auto cycle it's all same. Only this process 2 to 3 is different. You can apply different things to your cycles and you'll get those values. It's not that difficult. So yeah, I think I've taken one problem, but it has almost 5-6 problems in itself. And it will be better if you do this exercise for dual cycle also. Because I think auto cycle will be easier if you have done for diesel. But for dual cycle, it will be slightly tedious because there is heat addition at constant pressure as well as constant volume, and you need to, there will be one ratio there. I think it is explosion ratio or something. So you have to take that into account and take that definition into account and repeat the same exercise. Calculate pressure, volume, temperature at all 5 points. In dual cycle, there will be 5 points. So you do that for dual cycle. Calculate PVT at all points. Even if it is not asked in the question, you can do that. That will give you a whole idea. And then you calculate what is the net work output and what is the net heat addition. There, the heat addition will be there will be two terms, because one term will be at constant volume and one term will be at constant pressure. So that summation you have to take. Then there is efficiency formula, which will be it's actually cumbersome. The second term, it is a big term, I think, there. So you should know that also. So that's how you should do it. So today actually I have to go somewhere. So I'll not be able, I want to take more problems, but I think I'll not be able to. So yeah, I will stop here today. We are almost 6:55. So if you have any questions regarding previous assignments, you can ask, or if not, we can stop. Or anything regarding this class also, if you have any doubt, you can ask, or we'll stop. Anything, Narendra? Priyanka?
No questions, sir. Okay. Thank you. Thank you very much, sir.
No,
Everything,
sir.
everything is okay with your assignments?
Yeah, sir.
Okay, fine. Priyanka, is everything all right on your side?
Yes, sir. No doubt, sir.
Okay. So shall we stop today?
Okay. Okay, sir.
Yes, sir. Thank you, sir.
Okay. Thank you all for joining. We'll stop
Thank
here
you.
today. We'll wait next Tuesday.
Okay.
Okay. So yeah.
Okay, sir.
Have a good night and yeah. Bye.
Good day, sir.